The conversation begins with Planck saying to Schrödinger that he's heard of a new idea, asking what Schrödinger knows about quantum computing and quantum computers. Well, according to Jack D. Higgery's book, Quantum Computing: An Applied Approach, a quantum computer is a device that leverages specific properties described by quantum mechanics to perform computations. The same book later states that these properties of quantum mechanics allow for the computer to make use of different quantum states, including superposition and entanglement. These quantum states are what set quantum computers apart from generic binary machines. According to TechTarget.com, superposition is the ability of a quantum system to be in multiple states at the same time until it is measured. This therefore allows for a system to no longer be restricted by just 1 or 0. Their bits can be in a superimposed state. Another way to think about superposition is with the thought experiment of Schrödinger's cat. This is where a cat is placed in a box with a tiny bit of a radioactive substance, and when the radioactive substance decays, it would trigger a Geiger counter, which causes the poison to explode and release, killing the cat. As you don't know when or if the poison has been released, the cat can be thought of as both dead and alive. You will only know what it is until you open the box. By referencing science daily, we can deduce that quantum entanglement is a quantum mechanical phenomenon in which quantum states of two or more objects have to be described with reference to each other. Even though the individual objects may be sparsely separated, this still means that objects can be linked and entangled together and measure as the same state regardless of whether they're separate from each other. Schrödinger questions how this can be possible, to which Planck replies, qubits. Planck says that on a practical level, these qubits make quantum computers more powerful than our current computers. According to PC Mag, a qubit, or quantum bit, is a unit of computation in a quantum computer. The qubits can be in a superimposed state, which means multiple states at the same time, measured by electron motion and direction. Unlike classical bits, qubits are not used for storage. Data are transferred to qubits for computation and then read out for answers. Rather than charge or pulse of electricity in a bit, it is in the electrons in the qubit that are manipulated based on the laws of quantum mechanics. So to confirm what Planck said, qubits do make quantum computers more powerful than traditional binary computers, as confirmed by educba.com. When bits storing information of binary digits, qubits store a combination of binary digits, which helps the qubits in quantum computing work 3 times faster than conventional computer systems. The information stored and the data transfer is huge, which helps to transfer the information faster. Schrödinger then asks if these quantum computers could break current cryptographic algorithms. Cryptography is used to make messages unintelligible to any person who is not authorized to receive it. This is achieved by combining the messages with some additional information known as a key. A cryptographic algorithm that quantum computers could exploit is RSA algorithms. Modern computers use it to encrypt and decrypt messages. It's an asymmetric cryptographic algorithm. Asymmetric means that there are 2 different keys. This is also known as public key cryptography, because one key can be given to anyone and the other must be kept private. The algorithm is based on the fact that finding the factors of large composite numbers is difficult. When factors are prime numbers, the problem is called prime factorization. It's also a key pair, public and private key generator. RSA encryption is so secure with modern traditional computers as it's very difficult for them to find prime factors of a large number. The current best methods to achieve this are to guess a number that might be a factor, check if it is, and if it isn't, pick a different number and try again. The reason quantum computers could change this is to do with Shor's algorithm. Shor's algorithm is a prime factorization algorithm which would allow quantum computers to find prime factors of large composite numbers. This would help decrypt RSA encryption. So if we know all this, why don't we have quantum computers? Well, after reading an article by The Conversation entitled "A Quantum Computing Future is Unlikely Due to Random Hardware Errors," I found out some of the issues are noise and error correction. The mathematics that underpin quantum algorithms is well established, but there are daunting engineering challenges that remain. For computers to function properly, they must correct all small random errors. In a quantum computer, such errors arise from the non-ideal circuit elements for the interaction of the qubits with environment around them. For these reasons, the qubits can lose coherency in a fraction of a second, and therefore the computation must be completed in even less time. If random errors, which are inevitable in any physical system, are not corrected, the computer's results will be worthless. This is what makes quantum computers so hard to develop, and why we don't have working quantum computers yet.